Good evening. This is the third lab for Physics 2211. Let's jump into it. So the purpose is that given the mass of a star and its orbit around a black hole, we have to find the mass of the black hole, and then after that, given the previous information, the mass of both the star and the black hole and its orbit, you have to find out how fast a spaceship must travel to leave a planet and get close to a black hole without crashing to either. And so the principles in use, it's the Newton's second law, the universal law of gravitation, the velocity and position update formulas, and the parallel and perpendicular force formulas. And so the first part, the initial conditions are the gravitational constant of 6.7 e to the negative 11th, and then the mass of the star, 2 e to the 30th, then delta E, which is 1 day, 24 hours, times 60 minutes, times 60 seconds, and then the start of T, which is 0. And there we have the force of gravitation equation, which is the gravitational constant times first mass times second mass over r squared. And so part 1, computation, we have to figure out the initial and final momentums, which we can find using the initial velocities and the final velocity times the mass of the star. And then we have to figure out delta V and delta P, which is just V final minus V initial and P final minus P initial. And then we have to incorporate that into Newton's second law, which is dP dt over delta P times divided by delta T. And then F net just equals dP dt. And then F net parallel, you have to do dP dt over this magnitude to find P hat, and then just do the magnitude of P final minus the magnitude of P initial over delta T. And then for the perpendicular, you can just subtract it from the F net total minus F net parallel to get F net perpendicular. And so the mass of the black hole, after doing that, we could input the data that we got from the computation with our initial constants. And in order for the orbit to make sense, the black hole would have to have a mass of 1.65 e to the 34th kilograms. There's the orbit right there with the perpendicular force and the parallel, you can barely see there. And so for part 2, the initial constants are the mass of the black hole, which we got from the previous initial part, and then the gravitational constant, and then both the masses of the planet and the ship, and then delta T again, this is 1 second this time, and then the start again 0. And so the computation, you basically have to figure out delta R given for each of these. You have to figure out, basically use the equation of the gravitation for each, the black hole on the planet, the ship on the planet, the black hole on the ship, and then the planet on the ship. So delta R, R hat, and the force of gravity for each, and then you can figure out the net force overall on the planet by the ship and the black hole by adding both of those values up. And then as well for the F net on ship, you just add the force of the planet and the force of the black hole on the ship together to get F net on the ship. So the position and velocity update formulas, you just use both of those for each to get the initial velocity. And then after trial and error, I figured out that the initial velocity in the x direction was negative 3.85 e to the 7th, and then in the y direction 2.85 e to the 6th, to basically get close enough to the black hole without crashing into it and then exit the system. And that's the planet here in cyan. And so what does it mean? Basically, even though they are related, the net force and the rate of change of momentum are not the same. Do not mean the same, even if they do have the same value, because they are proportional values that point in the same direction, but they hold different meanings. And so the same can be said about each other's parallel and perpendicular values. And so what if, to achieve a circular orbit around the black hole, the ship would have to lift off from the same planet at a slower x speed, roughly similar to its y speed, but with enough speed to allow the black hole's gravitation to pull it around but not into the black hole. basically when we exited the solar system, we had a much larger negative x direction value, and so we could basically slow it down to the point where it points upwards and kind of gets brought into orbit around the system by the black hole. It could achieve circular orbit. And so yeah, thank you.